All right, so in this lecture and also the next one, I'm going to cover chapter 7, which is mostly about steady state errors. So, so the goals of these couple of units, lecture units, include to find a steady state error for a unity feedback system. You're going to specify a system's steady state error performance. You're going to design the gain of a closed loop system in order to meet a steady state error specifications. Going to talk about how to find the steady state error for disturbance inputs, and eventually going to find the steady state error for non-unity feedback system. So these are going to be the main topics that I'm going to talk about uh, related to steady state errors. So now I often use SS just to refer to steady state, and so I sometimes use SSE throughout the lectures from now on, which refers to steady state error. So let me first define what the steady state error is. So the steady state error is basically the difference between the input and the output of a system for a given test input as time goes to infinity. So the test inputs that are used for steady state error analysis and the design are actually shown in this table. So we can have a step input, a ramp input, or a parabolic input. So in time, in terms of as a function of time, this step could be just represented by one. And remember that we're just dealing with causal inputs or causal function, meaning that for any negative time instant, they would be like the value of this function would be 0. So so when we're talking about the value, the value of the function in time domain, we're just referring specifically for what the value they give us for t greater than or for t greater than 0. So for a step, it would be just 1. For a ramp, it would be just t. For a parabolic function, we specifically talking about 1/2 of t squared, but not t squared. So now in Laplace domain, for a step function, the Laplace transform would be 1 over s. For ramp, it would be 1 over s squared. And for 1/2 of t squared, it would be 1 over s cube. So now, if you assume a position control system where the output position must follow the input commanded position, we can make some physical interpretation of these three test waveforms. For a step, it's like this function, the physical interpretation is that this is like a constant position that you want to track. For this one, it's going to be, for ramp, it would be constant velocity, and for parabolic function, it would look like a constant acceleration that you want to follow. So now in this slide, I have shown 3 different test inputs for steady state error analysis and design. In fact, let's just assume that you have a tracking system installed on the Earth, like on the surface of the Earth, and you actually want to track 3 different things. One would be just a satellite that are just stationary targets. The other one would be just a satellite that orbit at a constant velocity, and the other one would be the accelerating missile. So basically, for each of these 3 targets, the reference would be different. For this one, for the first one, it would be position. For this one, it would be velocity, or simply just a ramp function. And for this one, which is acceleration, is what you really want to track. It would be something like a parabolic function. So now in this slide, you see how to evaluate the steady state error. For example, if you consider as a test waveform, as a test function, you consider a step input. And let's say you have 2 different outputs coming from 2 different systems. Output 1 eventually reaches the same input or the same desired input, and therefore here your steady state error is actually going to be 0, because the difference between the output 1 and input, when it gets to steady state, is going to be 0. For output 2, you see that it's going to get to steady state, but there is going to be a steady state error between output 2 and the desired input, and this is going to be your steady state. Steady state error. So now if you consider a ramp function, here for this illustrated example, I have considered three different outputs, output 1, 2, and 3. So you see the output 1 eventually going to reach the same slope of increase associated with the input, and of course, as you see, the difference between this input, this desired input, and the output 1 eventually is going to be 0, and that's why we have here a 0, what is called tracking error, or a 0 steady state error. And then we have second output, output 2. So it actually starts going up, and eventually it's going to reach the same slope of increase as your input, but it's going to maintain a difference, a constant difference even at steady state. So in this case, we say that we have a constant bias, or a constant steady state error between output 2 and your desired input. And then of course we have here output 3, which is not even, it's going to increase, but it's going to increase at a different rate or different slope than your desired input. So in this case, we say that the your output 3 is eventually going to diverge from your desired input. So now the next thing I'm going to talk about is how to calculate the steady state error for unity feedback. So I'm actually going to calculate this steady state error in general in two ways. One would be to find the steady state error in terms of the closed-loop system transfer function T of S, and another one is going to be in terms of, calculation of steady state error in terms of the open-loop transfer function G of S. So now let's just put your open-loop system G of S in a unity feedback configuration or architecture as you see it here. So if you really want to represent this in terms of closed-loop transfer function, remember that this whole thing is going to be replaced by just T of S, which is your closed-loop system transfer function. So the input to your closed-loop transfer function is R of S, and the output is C of S, exactly what you see here. And then we have this, what is called tracking error. And the tracking error is really the difference between R and C, and that's what you see here. So now really this is just a redrawn version of this unity feedback configuration. Here everything is just expressed in terms of G of S. Here you have T of S, and of course you have here E of S, which is just like here. That's the difference between R of S and C of S, just like here. So now to calculate the steady state error, so now this E of S is what we call tracking error, or just simply error, which is the difference between R of S and C of S. So really, if you just do very simple math, so the E of S is R of S minus C of S, but C itself is T of S multiplied by R of S. Okay, so then this E of S is going to be R of S multiplied by 1 minus T of S. And if you remember, in linear systems, we defined or we had used what is called final value theorem, which tells you that for a signal E, when it gets to a steady state, meaning E of t when t goes to infinity, this is actually going to be equal to the limit of S multiplied by the Laplace transform of E of t, which is capital E of S, when S goes to 0. And of course, we had one fundamental, not really assumption, but rather a requirement here in order for the final value theorem to hold true. And that was that we have to make sure that E of S is a stable transfer function. And that is why we only confine our conversation about the steady state error only for systems that are stable. Okay, so we only define a steady state error for a stable system, because otherwise it's just going to diverge, and obviously your steady state error is just going to go to infinity. So those are not the cases that we are interested. We are only interested in stable system. For stable systems, like I said, we can have this final value theorem that just tells you that E of t when t goes to infinity can be calculated by just taking the limit of S, which is a Laplace variable, multiplied by E of S, which is the Laplace transform of E of t when S goes to 0. So now if I just take this E of S that you see here and just plug it back here, we're actually going to end up with these equations. So we have So in terms of T of S, the steady state error, so that E at infinity is really going to give you the steady state error. So that's going to be calculated by taking the limit of S multiplied by R of S, which is the Laplace transform of your input R, multiplied by 1 minus T of S. And of course, T of S here is your closed-loop system transfer function. So as you see here, there is, of course, a trace of transfer function as well as R of S, which tells you that the steady state error is dependent on what is your input function, R of T, whose Laplace transform is R of S. So the next thing I'm going to talk about is really limit our conversation into 3 different categories of functions. And so those would be step functions, ramp functions, and also parabolic that I earlier talked about. So now, but first, let me just talk about how to express the steady state error, or how to calculate the steady state error in terms of G of S, not T of S, okay? So now, if you remember T of S, which would be the closed-loop system transfer function for unity feedback, would be just G divided by 1 plus G. So now, if you go back a couple of slides here, so if for T of S, you just replace it by G of S divided by 1 plus G of S. So then 1 minus T would be just 1 over 1 plus G of S. And therefore, the steady state error would be taking the limit, or would be calculated by taking the limit of S, R of S, divided by 1 plus G of S, when S goes to 0. So now we have 2 different representations for calculation of steady state error. One would be in terms of the open loop system transfer function G of S, and the previous one was in terms of the closed loop system transfer function T of S. But as you see, both of these are actually dependent explicitly on what function you want to track, R of S, basically. So now, in the next few minutes, I'm going to talk about different different test function or test waveform. So the first one would be step input. So for a step input, the R of S or the Laplace transform of the step input is just 1 over S. And if you plug it back into this equation, so if instead of R of S, you just replace it by 1 over S, you're going to end up with this. So S multiplied by 1 over S divided by 1 plus G of S. So S multiplied by 1 over S is just 1. So really you have to take the limit of 1 over 1 plus G of S, or just 1 over 1 plus limit of G of S when S goes to 0. So now the limit of G of S when S goes to 0, this is actually called the DC gain that we talked about it a couple of weeks ago, I think, when we were talking about the second order transfer function. So this is called DC gain. Of course, because this is just simply associated with the gain of the system at DC, meaning at 0 frequency. Okay, so this is called DC gain, or we also give another name to it in the context of interpreting different test function. This is called position constant. So this is called position constant, or just simply shown by K sub P. So that just tells you that if you have a step input, your steady state error would be calculated just simply by 1 over 1 plus Kp, and the Kp, which is defined as, well, which is named position constant, is just going to be calculated using this equation, just by taking the limit of G of S when S goes to 0. So this is how you will calculate steady state error to a step input. Okay. So now, in order to ensure that you have a 0 steady state error, so when you want to have a 0 steady state error, so your Kp should really go to infinity. Basically, the limit of G of S when S goes to 0, so this limit should go to infinity. What does that mean? It means that your G of S, which is your open loop transfer function, must be of this form, because you must have at least one S in the denominator. So when you take the limit of G of S when S goes to 0, the G of S goes to infinity. So of course you can have an S, S squared, S cubed, etc. But you definitely have to have at least an S, at least just one S in the denominator. So, and of course, an S in the denominator represents an integrator, or simply means you have a pole at S equal to 0. So, so basically, if you do not have a pole at S equal to 0, that means that the limit of g of s when s goes to 0 is just going to be a finite number, and therefore you're going to have a non-zero steady state error. So now let's talk about ramp input. So for ramp input, if you remember, the Laplace transform was 1 over s squared, and if you just plug it back into that equation, e to the power of, the steady state error would be just the limit of s multiplied by r of s, so you get 1 over s divided by 1 plus g of s. So if we just bring s from this numerator to denominator, it would be limit of 1 over s plus sgs. So now this is really going to be equal to the limit of, so if I just expand this a little more, so really this is just going to be the limit of 1, this is going to be just 1 over limit of s plus s g of s when s goes to 0. And of course, the limit of s is just going to be 0 because s just goes to 0. So you're just going to end up with what you see here, which is just 1 over limit of s g of s. So I'm just going to erase all this. This is, sorry. All right. So now, and of course, so now for a ramp input, your steady state error will be 1 over limit of s g of s. So now we now define limit of s g of s when s goes to 0 as what, as a velocity constant. And therefore your steady state error to a ramp input is going to be just the inverse of this velocity constant, kv. So now in order to have a 0 steady state error to a ramp input, you must ensure that kv goes to infinity. And when kv, which is this guy, goes to infinity, so this now implies that your g of s must have at least an s squared in the denominator. Basically, you must have 2 poles at s equal to 0. So when you multiply that transfer function by s, in the s, one of the s's in the denominator is actually going to be cancelled with the s here. So you still have like the s multiplied by g of s still has a single s in the denominator at least. So when you take it, so when you let s go to 0, so the limit of s g of s becomes infinity, and that's the condition that you must satisfy in order for the steady state error to a ramp input to be equal to 0. So really this is explained in better terms here. So to have a 0 steady state error, you must make sure that your velocity constant limit of s g of s when s goes to 0 tend to infinity, which implies that there should be at least a double integrator in g of s, meaning you must have at least s squared in the denominator. So you can have s cubed, you can have s to the power of 4, 5, etc. But you must make sure that you have s squared in the denominator. So now if you do not have, so if you do not have an integrator in g of s, what does that mean? So if you do not have an, so if you do not have that, then when you take a limit of s g of s, exactly because you do not have any integrator in the g of s, so the limit of s g of s is just going to be simply 0. And therefore, since the SSE or steady state error to a ramp input was just 1 over this limit, so it would actually tend to infinity. It means that your output with respect to your reference input, which was a ramp input, would be diverging. So now if you now consider the parabolic input, meaning that your R of S would be 1 over S cubed. So steady state error would be same equation, S R of S divided by 1 plus G of S. Now the R of S is 1 over S cubed. So it would be limit of 1 over s squared, and the square you're just going to bring it to the denominator, so it would be s squared plus s squared g of s. So the limit of s squared when s goes to 0 is just 0, so you just end up with limit of 1 over s squared g of s. So now you name limit of s squared g of s when s tends to 0 be acceleration constant. Okay, so now when you have a parabolic input, your steady state error is going to be calculated by 1 over Ka. And again, Ka is just acceleration constant that can be calculated like this. So now again, in order for you to have a 0 steady state error to a parabolic input, you must make sure that this Ka goes to infinity. And when Ka goes to infinity, which is limit of s squared g of s when s goes to 0, that implies that you must have triple integrator in the denominator. Well, you must have a triple integrator in g of s, which means you must at least have s cubed term in the denominator of g of s, which also implies that you must have a pole at s equal to 0 with the multiplicity of at least 3. And that's exactly what you see here. So to have a 0 steady state error to parabolic input, you must make sure that g of s has at least 3 integrators, meaning that the pole at s equal to 0 is repeated at least 3 times. All right, so now I talked about all these things, but in order to really unify my conversation, what I'm going to do is just to discuss what is called system type. So now, what is the system type? So really, the system type is going to be, so if your open loop system transfer function g of s can be expressed this form, and so you, in the denominator, if you have s to the power of n, so the value of n, or basically the number of pure integrators in the forward path or in the open loop system transfer function, is what you call system type. Of course, if you do not have any integrator, which, so, well, if you do not have like a term like s or s squared in the denominator, it means that the system type is just 0. If you just have a single integrator, then the n is going to be 1 and system type is going to be 1, and etc. So now this table really ties the concepts of steady state error and also those constants, velocity constant, position constant, acceleration constant, which often also referred as static error constants. So Kp, Kv, and Ka, so these are also referred to as static error constants. So this table really ties the concept of steady state error, this position, velocity, and acceleration constants, as well as the system types together. So now, just to summarize what we have discussed so far, if you have a step input, so the formula to calculate the steady state error would be 1 over 1 plus Kp. So if your system type is type 0, meaning that if you do not have any integrator in the denominator, your Kp, which is the limit of g of s when s goes to 0, is just going to be a constant number, and therefore your steady state error is going to be 1 over 1 plus Kp, which obviously is going to be a finite number. But now if your system is type 1, it means that you have an integrator in the denominator, and therefore your Kp is going to be infinity, and therefore your error is going to be 0 according to this equation. And if the system is type 2, so the static error, which is your Kp, is actually going to tend to infinity again, and the error is going to be 0. And for any higher type, it's still going to be the same. Kp goes to infinity, and the error is going to be 0. But now if you have a ramp input, the equation in order to calculate the steady state error would be 1 over Kv. If your system is type 0, then your Kv is going to be equal to 0. And again, Kv now is the velocity constant, and therefore your error is going to infinity. But if your system is type 1, meaning that you have a single integrator in the denominator, the value of Kv is going to be constant, and the error is just going to be the inverse of this Kv. But now if your system is type 2 or higher, the value of kv, velocity constant is going to be infinity, and therefore your steady state error is going to be 0. But now if you have a parabolic function like 1/2 of t squared, the equation that you can use to find the steady state error is now 1/ka, and ka is the acceleration constant. If your system is type 0 or type 1, your ka is going to be 0, and your error, your steady state error, would be infinity. But now if your system is type 2, meaning that you have a double integrator in the so you have a double integrator in the forward path, or just simply in your G of S, or simply speaking open loop system transfer function, your your ka is going to be a constant number, and your error is going to be 1/ka, which means it's a constant number. But now if you go any higher than type 2, your static error is going to be, so your ka is actually going to be infinity, and your error is going to be 0. But that's not really something that you see. But if you go type 3, for all of these, your static error constants are going to be infinity, and your errors are actually going to be 0. So the next thing I'm going to talk about is the steady state error specification. So the static error constants, basically the position constant, velocity constant, acceleration constant, those kp, kv, and ka that we have discussed in the past few minutes. So those constants can be used to specify the steady state error characteristics of control systems. So just like the damping ratio and the natural frequency and settling time and the peak time and percentage overshoot that we had discussed before for describing or for representing second order systems, in particular specification of the time response of the second order system. Here we can also use kp, kv, and also acceleration as specifications for a control system steady state error. So so we're also going to soon see a wealth of information that is contained within these specifications of a static error constant. So now, so just as a very simple example, if someone gives you a control system, and you also provided with a specification that kV is equal to 100. So whenever you're given like these acceleration constant, velocity constant, or position constant, so the first thing that has to come to your mind is that, or should be, that the system is stable, because these steady state error specifications are only defined for stable systems. And if you go back here, so we define kV because for kV is actually defined to be a constant number only for type 1, and of course when your input is a ramp function. So now going back to this example, so you can figure out that the system is going to be of type 1, meaning that you definitely have just s to the power of 1, or s in the denominator of the forward transfer function, or g of s, and your test signal is a ramp function. And of course for ramp input, if you remember, the steady state error would be 1/kV, and so since kV is 100 here is given, so then the value of steady state error is going to be 0.01. So in the next unit of this lecture, I'm actually going to give you a few examples that just cover what I just lectured about.